So we have built our single particle theory, and we've calculated the probability amplitude that if a particle is released from the origin at x is equal to 0 and allowed to evolve for a time t, according to our Hamiltonian, that we will detect this particle at a position x. Denoting the magnitude of x by r, it means that the particle traveled a distance r in a time t. If r is greater than t, then because we've set the speed of light c equal to 1, it means our particle traveled faster than light. And we guessed that the probability amplitude should vanish because our particle cannot move faster than light. Actually, the answer that we got is not 0. It looks like this exponentially damped amplitude, and it becomes more and more damped as r becomes greater and greater than t. So what this is telling us is there is a non-zero probability for our particle to move faster than light. Well, I'd just like to think about this answer a little bit and see if it really makes sense. So can we understand this answer that we got for this amplitude, and does it make sense given our experience? Well, I would argue that it does. There are situations in quantum mechanics where we've seen amplitudes just like this. So let me give you an example. So I'm going to draw some axes here. I'm going to label the x-axis just as x position. I'm not going to label the y-axis because I'm going to use it for a few things. So first of all, let me draw in a potential. So we'll imagine we have some potential well. And I'm going to consider the wave function of a particle that is trapped inside this well. So this is v of x. So this height over here is the height of the potential well. And I'm going to imagine that our particle has an energy, E, which is, so let's call this height V0, okay? And let's say our particle has an energy E, which is less than V0, okay? And I would like to draw the wave function for our particle. And I'm going to call the wave function of our particle psi of x. Now, inside the well, where the particle has no potential energy, it'll have kinetic energy. So inside the well, it feels no force, that potential is flat, so it just behaves like a free particle. So what wave function do we expect? Well, we just expect something like a plane wave. So an oscillating wave function, and the wavelength of those oscillations is set by the momentum, and the momentum itself is set by the kinetic energy. So knowing exactly what the energy is, I could work out its momentum and the length of those wiggles. Now, outside of the well, this is a classically forbidden region. Even if I turn all of my kinetic energy into potential energy, I cannot get enough potential energy to move outside the well. So classically, I could never move outside the well. But in fact, quantum mechanically, we know the answer is slightly different. The wave function can move out, but it's exponentially damped, okay, as we move out. So let's just summarize. This is the classically allowed region. And in this region, the wave function oscillates. Outside the well, so this is classically forbidden. And this region too is also classically forbidden. And what you find in these regions is that the wave function is exponentially damped. So I'm just reminding you of something that you're familiar with from your quantum mechanics course, which is that in the classically allowed regions, our wave functions typically tend to oscillate. And when we go to classically forbidden regions, our wave functions are typically exponentially damped. Okay, now let's come back to our problem. So for that, I'm going to draw a space-time diagram. So this is T. This is X. And the first thing that I want to put on this diagram are world lines of light. So here is one possible world line of light, just a line with a 45-degree slope. And here's a second possible world line of light moving in the opposite direction. Now, we can ask ourselves, what is the classically allowed region? So this region over here, in between the two blue lines, all of this region would be classically allowed. And if you study the integral that we found for our probability amplitude, inside this region, you find that as you shift the point x around inside this region, you find that the probability amplitude oscillates. Okay? And it's just like the oscillatory behavior of the wave function in the classically allowed region for the potential well. All of these regions beyond the blue lines, all of these regions over here, okay, all over here, this is all classically forbidden. If the particle wants to get to these green regions, it would have to move faster than the speed of light. And this is the area that this is the region for which we actually evaluated the integral, and we found that it was exponentially damped. So this is exponentially damped, and here too, it would be exponentially damped. So in fact, the behavior of our probability amplitude looks very reasonable. It's the kind of things that we have seen before in quantum mechanics, and we have no reason to doubt our answer. So we are really forced to conclude that our particle it really can move faster than light. And that's a problem. Why is it a problem? Why is this such a bad thing? Actually, this spoils relativistic causality. And that's going to be our next topic. I want to explain to you what relativistic causality is, and then I'd like to explain to you why a particle being able to move faster than light will spoil relativistic causality.